So in this session, we'll discuss about the how to write a 4-bit full adder or triple carry adder. Okay, so coding. Hope that you understood very well that the full adder and half adder using data flow modeling. So the 4-bit adder, the functional block diagram, and what are the I/O ports, what are the wires. So that fundamental concept you should know. Without knowing the black box details. So already I told you the black box details of full adder. Okay, so in the full adder, if you see so before writing the code, you should know the complete functionality of the 4-bit adder. So by using single bit adder. So this is a top model 4-bit adder. Okay, in the top model, so what are the inputs and outputs are specified? The 4 inputs, okay, A and B. So this is a 4-bit adder with the two inputs A 4 bits and B is 4 bits. So A and B are the 4-bit. Okay, for example, A is equal to 1010, B is equal to 1110. So A and B are the 4-bit inputs. And what are the outputs? A and 0. What are the outputs? The sum. So sum 0, sum 1, sum 2, sum 3. And what are the third input for the single bit adder? You know, C in. What is the output of this top model? Sum and C out. So this is a black box. The top model we have to define with the I/O ports list. Inside the top model, how the single bit adders are interconnected. So the gates are interconnected, the circuits are interconnected via wires. Nets are wires. So nets are called the keyword wires. You have to declare wire. Okay. So now remember that while writing the code, top model will give some name, specify the output and the inputs only. So here how many inputs? A and B. So A is a 4-bit and B is a 4-bit, and the third input C in, the 4 outputs and C out. You have to specify only this I/O port list. Then declaration of the ports. A and B are the input ports. C in is the input port. C out is the output port. Sum is the output ports. Then under which you have to declare if any wires. So C1, C2, C3 and all wires we have to declare. This is the top model. Inside the top model, what circuit we are using? The 4-bit adder designed using single bit adder. Okay, so single bit adder. The first I have to map you have to instantiate the 4-bit adder. You have to instantiate the single bit adder. How many times? 4 times. Single bit adder. I'm going to. So here in this top level model, this is a top model. So in that we have to instantiate the single bit adder. How many times? 4 times. Since it's a 4-bit adder, I'm going to use the single bit adder 4 times. So this is similar to in the microprocessor and all you studied subroutines. So what do you mean by subroutine? In the main program, the frequently used programs can be written separately. Okay, the frequently used programs can be written separately. In the main program, wherever it is required, you can call the subroutine and you can run the program. If you write, for example, 4 times, if you want to use the same program, instead of writing 4 times, okay, so you can call the subroutine and you can instantiate wherever it is required, so that the compilation time will be reduced, speed will be increased. Instead of writing 4 times in the main program, what is the concept of subroutine? Why we are writing the subroutine? So instead of writing the main program, you can write it as a separate program, subroutine program. You can call whenever it is required. Similarly, we have written the code for half adder, full adder. Okay. So in that, this is the bottom-up approach. There is a two methodology, top-down methodology and bottom-up methodology in the Verilog HDL. So in the bottom-up, if you want to design a 4-bit full adder, you need a full bit single bit adder first. If you want to design a single bit adder, you can design either data flow modeling or the gate level modeling using two half adders. You can write. Again, if you want to write a full adder, you need a circuit. Okay, in the gate level, half adder is required and gates are required. So these are called leaf cells. Leaf cells. So AND gate, OR gate, if you want to write, the library cells are already available. The primitive cells are already available. So using the primitive cells, for example, using a primitive cells, XOR gate, AND gate, we can write the half adder. Using half adder, I can develop a full adder. Using full adder, I can develop a 4-bit full adder. So this is your bottom-up approach. This is your bottom-up approach. You are building a 4-bit full adder using leaf cells, half adder, and 4-bit full adder. So that is called you are instantiating the models. Module instances is a top model. What are the models are instantiating? Here the model instance is single bit adder. Module is the top level model is my 4-bit adder. I given one source name, model name for the 4-bit full adder. This is a top level model. In this top level model, I'm going to use the single bit full adder 4 times. So that I have to instantiate. I have to instantiate my full adder. I have to call the full adder in the main program. So like separately, I written separately the full adder. In the main program, in the main top level model, I have to instantiate. I have to use this single bit adder. How many times? 4 times. So first time when I'm going to instantiate, I'm giving my option, my name. Okay, for my first full adder, same full adder only, but in the top model, I'm going to insert the first adder. So FA0. I'm giving some name. Okay, when second time I'm going to instantiate the same full adder, I given the name as for second full adder FA1. Third time when I'm going to instantiate, the third name is FA2 I'm given. Fourth time when I'm going to instantiate the same full adder with the name FA3. But whenever you are instantiating, the port mapping rules you have to follow in HDL. So if you are violating the port mapping rules, you will not get the output. That is the logical error you will get. See, while writing the coding, syntax error is different. Okay, syntax error is different. Logical error is different. Syntax error, if you write the statements, okay, if you forgot to put a termination, semicolon, so that will be the syntax error. Logical error, if you are mapping wrongly, then you will not get the exact output. So you have to follow the port mapping rules, okay, in order to get the proper output. For example, what may be port mapping rules? So you remember that in the full adder we have created already the top level model with the name FA underscore DF, open the bracket, outputs are specified, sum and carry followed by the inputs A, B, C, N. So in this 4-bit full adder, I'm going to use that full adder. Okay, I'm going to use that full adder. So how to instantiate this instance, full adder instance already available. How to instantiate? So you have to instantiate by the model instance name, that full adder name. Here I'm going to mapping with my full adder here FA0. So instantiate this with for FA0. In this, we have to specify the, you are going to map the ports properly. So while mapping for this first adder, what is the output here? So output is C1. In the top model, the C1 is declared as YS. But for particular this FA0, the output is C1. And what about the sum for this one? Sum 0. So when I map this adder, full adder in this top model, I have to specify I have to follow the same ports how I written in the single bit adder. In the single bit adder, I specified the output first S comma C. So in this, I have to specify S comma C1 followed by the inputs for this A0, B0 and Cin. Okay, if I'm not mapping properly, instead of sum and C, if you write C and C comma S, it will give wrong output. Understand? So the port mapping is very important to write the Verilog HDL. So most of the time the students, okay, will do the mistakes. The students will not get output due to the improper port mapping. So unless you give a proper port maps, you never get proper output. So according to this 4-bit full adder, ripple carry adder, so when I instantiate the first adder, so I'm going to use the same full adder only, but when I map here, the port mapping rules I have to follow. So the output is sum 0. The carries act as a output for the first adder. The inputs are A0, B0 and C. Since it is a 4-bit, I declared the inputs as vector type. Vector means multiple bits. So in a single bit adder, only two inputs, A and B, scalar. So in the 4-bit full adder, the A and B are the vector multiple bits. So that I'm using the square bracket in order to access individual. The square brackets I'm using. In the coding, I'll explain how to write. So this is a vector declaration. In the vector declaration, square bracket, then specify the MSB down to LSB. So MSB is 3 down to LSB 0. Similarly, sum is a scale vector type. The 4 outputs. So MSB to LSB 3 down to 0. Cin is a scalar. Okay. Cin is a scalar input and Cout is a scalar output. And you have to declare all the interconnected next declared as wires. Wire C1, wire C2, wire C3. This is single bit scalar or vector you can declare. Okay, dear. So this is a concept of full adder. Unless you know the concept, you cannot write the code because when I open that tool, I'm going to type a Verilog HDL code. How I can type? In my mind, immediately the 4-bit full adder comes into the picture. I have to visualize virtually in my mind what is the 4-bit full adder diagram. So what are the inputs, what are the outputs, what are the wires. If it is in your mind, then you can type your code with efficient Verilog HDL constructs. Simply without this basic fundamental knowledge, you cannot type the code. Simply copy the code from the notebook, okay, with the others code. Simply if you simulate .b file store, check syntax, you write the code, you give your own names for the inputs and outputs, wires, and you have to mod. So in this, the two concepts, what is a top module, and what do you mean by module instance? So this is a top module. Any concept they ask, you give it the example. So now these are the top module input IO ports, and this is the module instance full adder. I'm going to instantiate this full adder 4 times. That is a module instance. Okay. So with this concept, I can write the code. So now I'm going to write full adder, 4-bit full adder. New source, Verilog module. So 4-bit full adder, FOUR 4-bit full adder underscores. This is structural modeling. Structural modeling. Okay, dear. Next. So what is that Verilog model I am creating? 4-bit full adder using structural model. Finish. Now I created 4-bit full adder. No. Now I can go for the program. So module. See, I'm created. So I created 4-bit full adder structural model. Now in your with your mind. So the immediately the 4-bit full adder diagram, the top level model diagram should come into your mind. Virtually, you have to see the picture in your mind. So now with that, you can specify what are the outputs, sum, okay, comma, carry, comma, A, comma, B, comma, C, in. A, comma, sum, okay. So we can give here sum, C out, I can give A, B and C in. Okay, I have defined. What is that? Specify the IO ports, input output ports, IO ports of black box. Black box. Specify the IO ports of black box. So what are the black box outputs? Sum, C out, A, B, C in. Next, declaration on the ports. Now, what is the declaration? First output we declare. Declaration of output ports. So what is here? Which is the output port? Sum is the output port, C out. But what about sum for outputs? So for that vector declaration, square bracket, the MSB first you have specified 3 down to colon down to 3 down to 0 and close the bracket. So output 3 down to 0 and end with a semicolon. So declaration of here you can give the commands. Declaration of output ports as a vector declaration. Otherwise vector declaration. You can specify here vector, that means multiple bits of output ports. Okay. Next. Then what are the other output is C out is a scalar output. So that you can declare output C out end with semicolon. So here itself the vector and scalar you cannot be combined. Vector declaration separately. Scalar can be combined together. Okay. And what are the outputs? Sum. Here you have to declare sum. Output 3 down to 0 sum. C out is a scalar. Output C out. Similarly, is a now scalar. Okay. Is scalar output C out is declared. Okay. Next one. Out of terminal list, next to the inputs has to be declared. So what are the inputs? Input again 4-bit added. So 3 down to colon symbol, 3 down to 0, close the square bracket. So A also 4-bit, comma B also 4-bit. I can write the coding like this. Input A and again input B, you can write, but once if you know the constructs Verilog constructs, you can write in a single statement. Input 3 down to 0, A and B both are inputs. Now vector declaration of input ports, introduction of input ports A and B. Next, in this top model, already explained that in this top model, what are the wires? Before writing the code, wires we have to declare. So how many wires we have seen? So wires. So wire is a keyword. Wire. Like 3 wires inside that block. C in, C out. Then 3 wires we have declared. So 3 wires. 3 wires you can declare 3 wires. 2 down to 0. C2, C1, C0, C1, C2. 3 wires we declare. End with a semicolon. Okay. Then you can now body of the program. So body of the program 4-bit full adder, 4-bit full adder, 4-bit fulladder using structural modeling. Structural modeling. So for the structural modeling, so instantiate structural modeling. Let it be. Okay. First one, we have to instantiate the lower level models. Instantiate the lower level model. What is the lower level model here? Single bit adder. Lower level single bit adder. How many times you have to add? 4 times. Okay. So how to instantiate? That is called module, named as module instantiation. Module instantiation. Instantiation. So how to instantiate? Uh, so first module FA first added. So I'm going to call the same. What is the module instance name? With them, how do you do? Model instance name, we need fulladder FADF, that is FA underscore DF. So here in the top middle, my how I'm going to map it with my fulladder FA0, for example. Open the bracket. So in this FA0, in this I'm going to map it. So what is the diagram says that first mapping I have to give what is the output followed by, because here I have followed output followed by inputs. So for this fulladder, what is the first output? Here in the top model I given A, B only. So what is the output? Sum and Cout. So sum of 0, sum of 0, sum of 0, comma, okay. What is the output? Sum and C of 1, C of 0 here, C of 0, C of 0, okay, comma. These are the outputs of first adder, sum 0 and output is C0. Then the inputs are, you have to declare A of 0, comma, B of 0, and the third input for the first adder is C in. So if, in order to access the individual from the vector declaration, you have to use the, like C language, you have to use the square bracket to access the individual inputs. Simply should not type C0. You can type C0, then it will show the errors, syntax errors. So this is the port mapping rules you have to follow. End with it. So open the bracket, specify output followed by the inputs for my first adder. Then close the bracket, end with the terminate. So what is that? Module instance. Module instance name FA underscore DF. Module instance name FA DF instantiated for FA, my FA0, for my FA0 first adder, for my FA0 with proper port mapping rules. With the proper port mapping, that is star will do, slash star, with the proper with the proper with the proper port mapping rules. With the proper port mapping rules. So what are the port mapping rules? Slash. With the proper port mapping rules. So it's a single line command. This is a multiple line commands. Proper port mapping rules. Okay, which is followed in the your design FA data flow design. So here in that FADF we have followed SCABCin, not CNXCin. Okay. Then second flood. So now understood. Same you have to, how many times we are going to instantiate the full adder? 4 times. So now second full adder I am going to instantiate for the second full adder, my second full adder. Okay, so control V. So now same full adder I am going to instantiate for the second time. That second time my full adder name is FA1. So in that case, in this second full adder, the output is sum of 1. Then our carry is C out is here C of 1. Here the C is declared as a wire. Okay, the C is declared, so wire, no, here C, we forgot C, wire C. So C0 is a, C1 is a output for this one, but here the top one is a wire. So C1 and A1 and B1, and second, what is the input for this one? So for the second one, A1 C1 is the output. Okay, so this output will be C in input for this one. The C0 will be the input for the second adder. C0 is, so you have to remember the diagram properly. Okay, keep your diagram with you. Then see the how the signal flows. Okay, where you declared as wires, where you declared as input output ports. For the second full adder, the output of the first full adder C0 is the my input. So square bracket C0 is the input. Okay, then close, then terminate with the semicolon. So sum 0, C1, A1, B1, C0. Similarly, I want to instantiate the third full adder. Okay, so instantiate FA1 here. FA1 with the proper port mapping. Port mapping. If you do any mistake in the port mapping, you will not get the output. Then third, FA1. Next one. Okay, instantiate. Okay, instantiate the FA2 here. So FA2. So check, this is FA2. Here second full adder, the outputs are sum 2. So this is here C2, then C0, C, then A2, B2, and what is the output of the previous one? C1 is the input for this third one. Okay, end with the semicolon. Again, I'm going to copy the same. Next, last full adder I'm going to instantiate. Okay, full adder, same. Okay, so full adder. So you want to understand purpose, I'm writing like this. So next one, last full adder FA3. FA3. So sum is S0, S1, S2, S3, and here last output is C out. C out, no, by mapping. So last 4-bit single bit data FA3, sum 3 is the output, C out is the output, A3 is the input, B3 is the input, and last one is C out. C2 is the input. C2 is the third input. C2 is the third input and with semicolon. That's all. So this is only structural modeling of 4-bit full adder. Okay, so the commands I can give: design, a ripple carry RCA, ripple carry adder. It is a 4-bit ripple carry design, not n-bit. 4-bit replicatory adder using structural modeling, or you can say it's a gate level modeling, like that they will say structural modeling. So instantiate create single bit adder 4 times. Okay, so now end. So module, this is a top level module name. You have to specify the uh, IO port list and declaration of the ports, whether it's a scalar or a vector. Then wire you have to declare. Then this is the body of the program. So structural modeling. So you are going to instantiate the four single bit adder 4 times. So single bit adder coding already written. Wherever it is required, you can instantiate with that model instance name, same name. But I am mapping here for FA0, FA1, FA2, FA3. So you have to follow the port mapping rules. What you have followed in the data flow in modeling for full bit, single bit adder, same sum comma C out comma A comma B comma C in. So if you interchange all this, then the logical error will show. You do some mistakes and verify. This is exactly how to do. I saying if you if you find any mistakes, it will show the errors in the console window. You can debug and you can simulate. Okay, this is a complete coding for the 4-bit full adder. Hope that now you understood the bottom-up approach. In order to design a 4-bit replicatory adder, first we design half adder, then full adder, then the single bit adder you can instantiate here. Okay, since I written data flow modeling, I instantiated directly the full adder. Otherwise, I can write the data flow model instead of data flow modeling. The full adder also can be written by using two half adders. Okay, so then if you instantiate in a full adder, it will call the half adder. Okay, so so at the beginning you learn the Verilog HDL construct thoroughly, because here in the coding itself, while writing the coding, so many Verilog constructs also I am teaching for you. So please kindly explore the Verilog HDL constructs very well and the syntax how to do it. Okay, then now I can save the program file, save. Once it is saved, I can go for the check syntax. No, check syntax, check syntax. So one error is, it shows one error. Line 3 port reference declares the input. Okay, see CIN. So I didn't declare the input CIN, so that you can declare the input. So I'm doing some mistake. That's why you can find out the. So see, since I forgot to declare the CIN input scalar declarations CIN. So I can give the comments input scalar declaration for the uh, input for the input for CIN. Okay, now I can say I can check syntax. Yes, I want to save the files. Now see failed again. So what found where line 8 expecting end with semicolon. I forgot the semicolon. See, all the syntax errors will show end with semicolon. Now I can do the check syntax. Yes, hope that it will be succeed. Yes, good. So see, in this age, I am 50 years of age. Okay, I am doing. So you people can do very fast if you know the concepts. So check syntax now succeeded. Then you can go for the synthesis report. Then you can see the RTL schematic. See A, B, 3. This is a 4-bit adder, 3 down to 0. Some only this is a black box chip. IO port declarations. Then inside, if you click the gate level, you can see all the gate levels. You can see, these are the gate level RTL schematic. While the documentation, you can take the printout of this RTL schematic with your coding, test bench coding, and simulation waveform. That with the test bench, how to verify the output result, that we'll discuss in the next session. Okay, thank you.